In 1971, Yamaha developed a 5-day seminar of very high-level piano technology called the Little Red Schoolhouse. The response from the technical community to this seminar has been overwhelming and continues to the present day. However, the number of technicians that can be reached by the seminar method is limited. With this in mind, we have decided to put this material in the video format to share the information with more people. This series is dedicated to the piano technician. Service is not performed on a piano just when a defect is found, but should be considered a vital part of the piano. Without service, the piano loses its ability to create fine music, and without the piano, the world of music loses an essential tool of creativity and expression. Please note, this video series is not intended to be a home study course that replaces proper training. The intent of the series is to present technical information that is more correct, precise, and understandable than the material currently available to the piano technician. The piano action is just a machine, a group of levers and gears that respond to predictable physical laws. However, to make music with this machine, it is necessary to involve a human pianist. It is our intention to focus on the simple fact that the human element must be considered. The series is aimed at the practicing piano technician. However, it is our hope that it is presented in such a way that it can be beneficial to the beginning technician, the serious pianist, or just about any interested pianophile as well. The benefit to the piano technicians will be in expanding their ability to make the required compromises and adjustments to get the best performance from the piano. The benefit to the non-technicians will be an understanding of what regulation means and why it determines how the piano responds to the player. Without the background of the practicing technicians, the other groups will be at a disadvantage because much will be taken for granted. Further, non-technicians must realize and be warned that what they learn from these tapes is as risky in untrained hands as it is useful to the trained technician. In short, don't experiment without qualified help available. Hopefully, it is information that will allow the qualified piano technician to better service one of the most important, if not the most important, musical instruments ever devised. It is our pleasure to present Piano Technology the Yamaha Way, a master series. This is a program of progressive regulation and adjustment procedures necessary to allow the grand piano action to function correctly. However, before we get to the actual steps, it is necessary to lay a few ground rules so that it is easier to understand what will follow. First, we must have a consensus that the discussion will be devoted exclusively to grand action regulation and will not cover other fields, even if they are directly related to grand action regulation. Staying on track is very important, for the fields of piano technology are many, long and wide, and if we don't limit the scope of our discussion, it is difficult to cover the subject properly. For example, the condition of the average grand piano is such that other work in the area of preparation, repair, and refurbishing is necessary before action regulation can be successfully accomplished. Taking the average piano and bringing it back to condition would be a good subject for a video program, but it's not the subject of this tape. This means, for this program, you must ask yourself to think of an action that is already prepared, repaired, and refurbished, not the usual action condition you might find in the next grand piano you are called on to service. Or better yet, think of an action that is new, one of good quality and already in good working shape. With that sort of action, we can properly discuss regulation. Now for the next point. Where do we do the work? In the home or at a shop? There is no argument against a shop in the life of every piano technician. It is true that the shop is essential for major repairs, for rebuilding, for any preliminary work needed to be done on the regulation job. However, it is just as true that it is possible to do more accurate regulation at the piano than at the bench. In the shop, it's impossible for the technician to duplicate the exact situation that exists in a piano.
Even with the care and effort necessary to make a perfectly flat workbench for the shop, one finds that not all key beds are flat. And how do we set up to duplicate the string height of the piano back at the shop? Usually the target we use at the bench for the string height is a straight board, but the string line in each piano varies from a straight line. It depends upon the shape of the cast iron plate, which in cooling takes on a slightly different shape from one plate to the next. It's not difficult to prove that the only practical way to get the exact set of conditions that exists in a particular piano is to go to that particular piano and work within the conditions found there. In short, regulation as we view it should be thought of as customizing an action to perform at its best in a particular piano. If the job requires major repair, rebuilding, or refurbishing, it may be that a trip to the shop is called for. However, since the subject of this discussion is regulation and not repair, all regulation work as we define it can and should be done at the piano. This will allow us to limit our discussion to actual piano regulation, and I assure you that that subject is large enough. With that precondition taken care of, you can see that the idea of doing everything else in the confines of the customer's home can become a reality. Now, this approach has many positive ramifications. Not only do you have the exact situation to work with, you're more likely to have the advantage of the availability of the pianists to contribute their input. Technicians have labored too long under the false assumption that the responsibility of our job ends when we have completed a reasonably good job of making sure the piano is set up to a list of specifications given by the manufacturer. Now, while that is important, our real job is to make the pianist satisfied, and working on the piano is just the way we do that. Good communications with the pianist is essential for this level of workmanship. You will be able to save valuable time by having the ability to check each adjustment for accuracy immediately before proceeding with a large number of changes, only to find out later that the work was not done correctly. It is our belief, then, that all regulation can and should be done at the piano, and the information that follows will proceed on that assumption. It becomes your responsibility to think through the problems this creates, like where to put the case parts so they do not become damaged by your activities or the actions of the children or the animals, whether or not you need to carry a blanket to cover the piano in case you want to use the top of the grand as a workbench, and any measuring tools, jigs, and hand tools that might be of help. If regulating at the piano is a new approach for you, you will soon find that the positive values of communication, accuracy, and precision that are derived by working at the piano far outweigh any inconvenience you may find in preparing for it. Now for the preparation of the piano that may be needed before starting on the actual steps in order. Unavoidably, grand action regulation cannot be a simple matter of starting at a definite beginning place, proceeding through a precise list of steps, and ending with perfection without retracing any of these steps. The fact is, many steps have influence over others, and in some cases, it is something like tuning, where you need to have the piano in pretty good tune before you start to do the fine work, even if it means going over the tuning once or twice before you can start. In the case of grand action regulation, there are 3 points that should be checked for accuracy before starting on the first step in the textbook. Yes, all 3 will need to be rechecked, and most probably re-regulated later on when their number comes up in regular order. But it is still very necessary to have the big 3 in proper position before anything else is attempted. The first of these 3 points is the tension of the repetition lever spring. If the tension is too weak, it cannot support the weight of the hammer assembly, and this weight will depress the repetition lever until the jack is the total supporting member. This will complicate the ability to make an accurate hammer line and will keep the jack from returning to rest position. Check the repetition spring tension, and if too weak, adjust the spring for proper strength. For those of you that are not familiar with this adjustment, it will be described in great detail later on. The second point to consider is the distance between the hammer and the string. The average movement of the hammer is 5 times that of the key, and it is easily seen that this relationship has to be established early in the process, or it is impossible to make proper adjustments of the levers that are in between the key and the hammer. Also, it is necessary for the weight of the hammer assembly to be fully resting on the whippin and in turn on the capstan screw in order to depress the back of the key firmly into the back rail cloth. If the hammer to string distance is so great as to allow the hammer shank to be resting on the hammer rest rail or the cushion, the weight will be on the cushion and the key will not be pushed down firmly onto the back rail cloth. If this happens, the front of the key will be lower than it should be, giving the appearance of a key height that is not correct. Of course, if the only problem is that the hammer rest rail is too high, make the correction there if working with that type of action. Another area related to the hammer to string distance is the position of the knuckle, or roller as it is sometimes called. Only when the correct position is reached will the edge of the jack that is nearest the hammer be in the same plane as a line extending downward from the core wood of the roller. Otherwise, the line takes on a dog-leg bend, and it is very difficult to properly align the jack position with the core wood strip. Check the hammer to string distance and make the necessary regulation of the capstan, or perhaps the hammer rest rail, to achieve a good hammer line. The third point to check is the drop adjustment. The grand action is designed in such a way as to have the repetition lever stop its upward travel by contacting the drop screw just before the jack fully escapes from under the roller. When this adjustment is correct, immediately after let-off, the hammer will drop the amount specified and will stop when the roller touches the top of the repetition lever. If the drop screw adjustment is too high, the process of escapement by the jack will not result in the hammer dropping to the lever. Instead, the lever will continue its upward motion, carrying the roller with it, and push the hammer against the string. Check for the drop adjustment with the action in the piano and correct as necessary. Without drop, it is difficult to achieve correct let-off. With these 3 points in approximate position, we can now start with number 1 of the 37 steps of grand action regulation. It seems that the secret of building anything worthwhile starts with proper construction of the foundation. Without a proper foundation, it is folly to spend time and effort on the areas that will rest on that poor foundation. This point of having a good foundation for the action is a very important portion of the musical performance in the piano. Tone not only comes from the soundboard and strings, the manner in which the hammers hit the strings also affects the tonal quality. And for this you need a solid base for the hammers. Touch not only comes from correct leverage relationships, it also depends on this same solid foundation. The screws need to be tight so that the parts are securely fastened, which in turn will provide stability for the regulation, eliminate unnecessary noise, and make sure that the various parts can be in correct relationship to each other. In other words, create a firm, solid foundation. What would seem to be a very obvious step is often partially and all too often totally overlooked. The stability of the position of the action parts can only be achieved if the screws are properly tight. And certainly one of the requisites of a good job is that the piano can be used without the parts getting out of alignment as it is played. The noise created by the loose action parts is also a consideration. Every piano action, by its very nature, will have some noise, but any unnecessary annoyances should be avoided. And lastly, there are distance relationships that must be maintained. Especially important is the distance between the center pin of the Whippin flange and the center pin of the hammer flange. Since the two parts are on different rails, and the Whippin rail is usually adjustable, it is imperative that the screws be tight and maintain this relationship precisely. Now comes the question, how tight should the screws be? It is clear that the human has enough strength available to over-tighten, so when is enough enough? That is a difficult question to answer precisely without resorting to torque readings that are arbitrary at best. And more to the point, even with exact torque readings, what percentage of technicians would purchase and diligently use a tool that would make sure the exact torque was applied? To be practical, we must revert to attentiveness, skill, and past experience. The screws should be very snug, but without resorting to mechanical ways to multiply the physical advantage of the twisting force of the wrists. A piano has a lot of screws. Which one should we tighten? There are two distinct classes of screws with totally separate purposes. First, there are the regulating screws, which do not bind parts together, but rather adjust or regulate timing and the limits of the hinge units as they are put in motion by the piano keys. Leave regulating screws alone for now. We will cover them later in the series. The class we're speaking of here might be called binding screws, which serve to hold two parts firmly together in proper position. Of course, there's no use in having a screw in the piano anywhere if the screw is loose. So the answer is tighten all binding screws. It should go without saying that this means all accessible screws. However, since this is a discussion on action regulation, we will limit our thoughts to those screws directly related to the regulation process and ignore any others during this presentation, like plate screws, important as they may be. In that context, then, let's check first all the screws we can find on the action, which include the screws in the brackets, those in the hammer rail, those in the Whippin rail, and those under the keyframe. Next, tighten those screws in the damper rail which are left inside the piano action cavity after the action was removed. Doing the job is simple. Just center the screwdriver blade in the slot and turn clockwise until hand tight. Very snug, but not over tightened. If, on that rare occasion, you happen to find a screw where the thread in the wood is stripped, by all means correctly repair the situation and do not settle for a repair that is not as good as the original. I will not comment on the repair procedures for wooden action rails and assume you are well aware of those techniques. I will, however, make mention of the fact that there are pianos made with rails other than wood, and perhaps a few words would be of help. In the case of the metal alloy action rails, the possibility of the thread being stripped is very rare. Tests conducted on the material used by Yamaha in their action rails disclosed that the metal was about 10 times stronger than wood for resisting stripping of the threads. When the problem of a stripped thread in a metal action rail is found, the solution is simple. All that is necessary to repair such a situation is to replace the original screw with a screw of larger diameter. The hole in the flange is large enough to accept the larger screw, and the stripped hole in the rail is the correct pilot hole size for that next oversized screw. The screws are self-tapping, and thus the repair is completed by simply screwing in the correct oversized screw. To correctly perform this operation, the only tools you will need are correctly sharpened screwdrivers of appropriate sizes. A word about screwdrivers. It's too bad that the companies that make screwdrivers apparently do not know that screws have slots that have parallel sides, so they continue making screwdrivers that have tapered blades. Proper sharpening by hollow grinding the blade will produce a screwdriver blade with somewhat parallel sides that results in a much better tool. In the process of tightening all the screws, be cautious of these points. When twisting the screw, be careful that the attached part does not shift or otherwise move out of position. Do not apply so much force that the wood is compressed or that the thread is stripped. Don't let the screwdriver slip and mar the screw head or scratch the surrounding area. When tightening the screws on the underside of the key frame, it's necessary to stand the action on the edge of the back rail. If this is done with the action on the key bed, the drop screws are in position to possibly scratch the front beam, the finished beam in front of the tuning pins. Be careful not to allow this to happen. That takes care of the first step, tightening action screws. We now have an action that is stable, noise-free, and has the parts securely held in proper relationship with one another. We can now proceed to step number 2. The main purpose of the front rail is to maintain proper key position, and through the use of the front rail punchings, to stop the downward movement of the key when it has traveled the proper distance. An important factor in this area is that the rail must be able to move from side to side when the shift pedal is used, and yet remain in solid contact with the key bed. If the piano design did not include the shift pedal, as in the case of the upright piano, it would be possible to attach the front rail to the key bed by the use of screws. Since this is not the case, careful fitting of the front rail to the key bed is necessary. The reason for making sure this point is correct is to provide a solid foundation for the action, one that will support the forceful blows of the musician without producing any unnecessary noise, and at the same time give to the musician that solid feeling that adds to the security needed by all pianists. The entire action rests solely on the 3 rails found in the front, center, and back of the key frame, and those rails are, in fact, the foundation that the action is built upon. The correct end result is a condition where the underside of the front rail and the top of the key bed are touching each other along the total contact area. Perhaps a word or two about the construction of the key frame is in order. The basic approach is to have the 3 rails attached to each other by cross braces, each connected in a perpendicular fashion to the rails. This creates a key frame that is light in weight and yet one that is quite strong. The method of attaching those braces also supports the center rail slightly above the level of the front and back rail, and the front and back rails are slightly slanted upward toward the higher center rail. In other words, if you placed the key frame on a flat surface and viewed it from one end, you would find that both the front and the back rail are resting on the outside portion of each rail, and the center rail would be floating and would not contact the flat surface at all except through the bedding screws. The importance of discussing the construction details is simply to call to your attention that only a very small area of the front rail is in contact with the key bed, and any correction that needs to be made involves removing only a small amount of wood. If we position ourselves in front of the piano and focus our attention on the contact line between the bottom of the front rail and the top of the key bed, the correct situation would be that there should be no space anywhere along the contact area. Let's pretend for the moment that the front rail was curved with a slight upward arch, where only the 2 ends of the rail contacted the key bed, and a bit of space existed between the underside of the center of the key frame and the top of the key bed. It is obvious that the method of correction must be to remove some wood from the 2 ends to allow the entire rail to settle a bit lower. In that way, contact would be possible along the entire area. To make this adjustment, you simply use garnet paper with the cutting surface upwards to remove the wood from the bottom of the rail until all areas are in contact. Never remove wood from the top of the key bed while performing this step. It will be necessary to prepare the action before using the garnet paper strip. What you will want to have when you finish the preparation is an action with the keys removed but all other parts firmly attached in their proper place. To do this, we suggest the following procedure. There are screws in the feet of the action brackets. Most are positioned so that they are at 90 degrees to the wood surface. However, a few screws, usually on the front feet of the inside brackets, go into the wood at a slightly different angle, and these angled screws should be loosened first. These screws are inserted at an angle in order to better hold the action brackets from becoming loosened by the thrust created by the upward motion of the capstans, especially considering the tremendous force used to play fortissimo passages. Remove the hammer action. Remove the keys and replace the hammer action. Tighten those angled screws last. Because they are at an angle, tightening them first might move the bracket out of position. You will now have a completely assembled action except for the keys. Next, raise all the bedding screws until they no longer touch the key bed. Usually 3/4 of a turn in a counterclockwise direction is sufficient. The clearance can be ascertained by sliding a narrow strip of paper under the bedding screws. As long as the paper passes under the bedding screw without friction, the screw has been raised enough. In the case of some makes of pianos, a couple of bedding screws can be reached only from the underside of the action. Usually, needle nose pliers will be the tool necessary to make the adjustment on that type of action. At this point, the key frame should be resting only on a small area of the front rail and a similar area of the back rail. The bedding screws of the center rail should not be touching the key bed. The entire action assembly is supported between those 2 points, something like a bridge spanning a river, supported only by the portion of the bridge that touches the 2 banks of the river. Place the key frame and the action into the piano and install and tighten the key blocks in position. The key blocks, through the key frame pin guide, position the action forward and backward to allow the hammer to strike the string at the correct point, and also to put a very slight down pressure on the key frame guide pin. Some slight down pressure on the key frame pin is essential. With some pianos, the adjustment for the down pressure on the key frame pin is made by turning a screw in the key frame guide assembly itself. On other pianos, it's necessary to raise or lower the entire key block to accomplish this adjustment. Tap downward on the top of the front rail, listening for the character of the sound created by the tap. Where the rail is in firm contact with the key bed, a solid sound will be heard. Where the rail is not in contact, you will hear a somewhat hollow tap, indicating that the front rail was forced down and slapped at the top of the key bed. With chalk, mark on the front rail at each end of the area where the tap is heard. The process of sanding is usually best done in steps, a little at a time, in order to remove only the necessary amount of wood, and to save time by not making a mistake by going too far. Place the garnet paper with the grit upwards under the key frame in the areas that created the solid sound and pull the paper out, removing a small amount of wood from the underside of the key frame front rail. The tools necessary for the total procedure would include a tuning hammer or other tool capable of turning the bedding screws, needle nose pliers for some actions, garnet paper of fairly fine grit, perhaps 100 to 150, and chalk. While tapping with one's fingers is the usual procedure, it is possible to felt the end of a dowel or glue 2 hammers together to create a tool that can be held in the grip of the hand instead. If the piano is older, or suspect of having a key bed that is not perfect, it would be well to check the key bed itself for flatness in the contact areas and make any corrections that are needed. This completes step number 2. We should now have a front rail that is in solid contact with the key bed all along its length. The center rail, or balance rail as it is sometimes called, is a very important member of the action. It is, in the truest sense, the fulcrum on which the key pivots. As such, it must provide a very firm foundation for that fulcrum. Otherwise, any movement would be translated into a loss of power and diminished control for the pianist. It can be concluded that the height of the key is a result of 3 factors. Those factors are the height of the top of the back rail cloth, the thickness of the punchings under the key, and the height of the center rail itself. If the bedding screws are turned in a clockwise fashion too far, the center rail will be forced upward and raise the height of the keys. If the bedding screws are not touching the top of the key bed, and the weight of the keys is added at a later time, the rail will sag downward and the key height will become lower. It is our challenge to adjust the bedding screws from their position of being free and clear of the key bed as we left them in step 2, to a point where all of the bedding screws are just in contact with the top of the key bed. This procedure will lock the center rail at the height it has naturally settled to, with the weight of all of the parts on the key frame except the keys. I can't guarantee that this natural position is correct for every action made, but it does seem to work well for most. Checking the key height measurement supplied by the manufacturer against the key height that results using this method would indicate if change is needed. If higher key height is called for, and it appears to do so would require the use of very thick center rail punchings, a small amount of center rail lift can be accomplished by the use of the bedding screws. Care must be used, as too much downward pressure of the bedding screws will not only raise the center rail, but may raise the front rail as well. If the key height becomes too high as a result of using this method, it is possible to adjust the bedding screws with the extra weight of the keys on the key frame. Be careful here as well. If the adjustment is made with the extra weight of the keys, the usual key height will be too low, and extra punchings will be necessary. Extra punchings create a less solid key action, and as they pack with use, can result in loss of the precision you adjusted into the action. Starting without the keys on the key frame, the standard we are striving for with our method is to have the bedding screw contact the key bed, but with the slightest amount of pressure possible. If a bedding screw is very close, but just clear of the top of the surface of the key bed, a sharp blow applied to the top of the rail will force the bedding screw downward, and a sound can be heard as the screw touches the key bed. The correct adjustment would be to turn the bedding screw downward until it just touches the key bed, which can be verified by the change of character of the sound the sharp blow will produce. Instead of a tap, the sound will now become a solid thump or thud, indicating a solid connection between the bottom of the bedding screw and the top of the key bed. However, there are 3 different positions the bedding screw can have in relation to the top of the key bed, where a sharp blow will not create a tap. And of course, only one of those positions is correct. As just stated, if light contact is made, the screw is in the proper position and the sharp tap sound will not be heard. If the screw has been turned too far in a counterclockwise direction and the bottom of the bedding screw is quite a distance from the top of the key bed, a sharp blow will move the bedding screw downward, but not far enough to allow it to contact the top of the key bed, and thus the tap will not be heard, even though the bedding screw is certainly in the wrong place. At the other extreme, if the bedding screw had been turned in a clockwise manner, and the screw is now down so far as to put a lot of pressure on the top of the key bed, no tap would be sounding from a sharp blow, but an error in adjustment is evident regardless. Inspection based upon a sharp blow that does not create a tap is not enough. The following procedure will assure a correct adjustment. First, make sure that all of the bedding screws are not in contact with the key bed, just as we did in step number 2. For our purposes, we will use this bedding screw. However, it's important for you to start at one end of the action. Place a strip of paper under the first screw and turn the screw downward until the slightest friction can be felt when moving the paper. At this point, with the paper strip removed, a sharp blow will produce a tap. If by chance the sharp blow with the fingers does not produce the desired sound, remove the paper strip from the piano and continue turning the bedding screw in small increments until a tap can be heard. Lay the strip of paper aside. Continue turning the screw clockwise a very small amount and testing until the sound created by the sharp blow changes from a sharp tap to a dull thud. This test must be made without the weight of the tuning hammer on the bedding screw. If the screw has just made contact and is exerting very little pressure against the key bed, it will create the desired dull thud. At this point, the slightest lifting of the screw will cause it to tap again. This is our test to assure that only the smallest amount of downward pressure is applied. While repeatedly striking the top of the rail very close to the screw in question and hearing the solid no-tap sound, carefully take hold of the bedding screw with the thumb and index finger of the other hand and lift upward with a very slight force. The character of the sound should change to a tap immediately. If it requires much lifting effort before the tap begins, it is an indication that the bedding screw had been turned too far downward. Readjust the bedding screw as necessary to have the correct no-tap sound when your other hand is not lifting, and a tap being created when a very slight lift has occurred. Duplicate the procedure we have just completed on the next closest bedding screw. When correct, check the first bedding screw to see if there's been any change. If not, proceed to the third bedding screw, which is the next closest to number 2. Because of the strength of the action return spring and the sensitivity of this test, it's possible to have the action held slightly off the key bed and an incorrect sound being heard. To avoid this error, occasionally press downward on the top of the center rail while depressing the left pedal a couple of times. This will free the action from the position on the spring and assure that the action is in its most downward position. Continue across the action from bedding screw to bedding screw, being careful to always check all of the previously set screws before proceeding to the next. The action will only be played when the key blocks are in and tightened down, therefore you should do just that. And test all of the bedding screws again by striking near each to confirm the correct adjustment. For tools, you'll need a way of turning the bedding screws, like a tuning hammer, and perhaps a pair of needle nose pliers, and a strip of paper. Your finger can provide the sharp blow, or you can fabricate a dowel with an upholstered end or similar device to use instead of the end of your finger. This completes step number 3. We should now have an action adjusted so that all of the bedding screws are just barely in contact with the top of the key bed. We can prove this by the audible sound we hear as we tap the center rail in the vicinity of each bedding screw. Let's proceed to the next step. The technician should realize that the regulation and adjustment procedures that are done on the keys of the piano are not only for the action, but in a very real sense, those adjustments are mostly for the benefit of the pianist. The keys have been called the gloves of the pianist since they are the only part of the action that the musician contacts and are intimately involved with the creation process, sort of an extension of the fingers of the pianist. At the same time, the keys are simply sticks of wood and must somehow be positioned so that they stay in place and yet move in a stable and almost frictionless manner. The key pins and the key bushings provide that service. There are 2 key pins and 3 points on each key that need to be checked for proper fit. For step number 4, we will discuss only one of these points, the bushing surrounding the front rail guide pin. The purpose for this bushing is to allow the key to move up and down in a smooth, almost frictionless manner, and yet hold the key properly positioned. There should be very little side-to-side motion possible, even though the bushing should not touch both sides of the pin simultaneously. The measurement is taken by depressing the key completely and then moving it from side to side. The adjustment is correct when there is a small but definite movement. The actual measurement given by the factory is 0.3 of a millimeter. This would be difficult to measure exactly, but can be felt as a slight free movement as the key is moved from side to side. The procedure to follow is to remove the hammer action, replace the keys, and leave the hammer action off. With each key fully depressed, move the key from side to side to check this adjustment. Make sure that the movement of the key is being made at the front rail bushing. Movement at the center bushing can be misinterpreted as being at the front of the key. To make sure the key doesn't move at the center bushing, you can hold the key stationary by applying pressure on the key with the other hand. At the Yamaha factory, they check keys by moving from one to the next as fast as is practical, testing each key against the standard and at the same time comparing the movement of each key with the others as well. If each one is checked slowly, the standard has to be memorized. On the other hand, if one moves quickly from key to key, each key can be checked against the others as well as against the standard. It becomes easy to find the one that does not match, and by taking care of the most obvious problems first, the key movement becomes more uniform as you progress. In fact, we make great use of this system of comparing all regulation measurements against themselves whenever it is practical. In some respects, having the same amount of side-to-side movement in all keys is more important than having some of the keys perfect and others just close to correct. There is only so much time available to do any job, and comparing the existing measurements with each other is not only an easy way to find those that are grossly out of position, but a very accurate way to produce the best results. This check will reveal that the space is either correct, too tight, or too loose. If the fitting is too tight, first check the condition of the front rail pin. If it is turned, rotate it back to the position where it is straight, meaning that the pin's oval shape symmetrically matches the hole in the key. In this position, it will present the least amount of friction as the key is used. Before turning the front rail pin, remember that any time a tool is used, there is the possibility of damage. For the best protection against creating a problem, lift the punchings and place the tool at the base of the pin. With the tool placed in this position, the punchings will cover the mark and keep the bushing from being damaged. Also look for corrosion or any other friction-causing problem and remove the source of the problem. Metal polish works well for corrosion. With further checking, if the pin is still just a bit tight inside the bushing, using the broad wedge of the Yamaha CF tool inside the bushing area can be recommended, for minute adjustment and great control is possible with this tool. If the amount of tightness is more than minimal, use of the key easing pliers is recommended instead. But in the usual case, you'll find that the side-to-side movement is too large. And in that case, one can use the broad wedge of the Yamaha CF tool in a different way and compress the wood on each side of the hole. As the wood is compressed, it will make the hole a bit smaller. Obviously, this method of compression can only be used when a small adjustment is needed and doesn't take the place of rebushing. As a last resort, one can turn the front rail pin a bit to present a wider profile of the pin to the inside of the hole. Turning the pin was never envisioned by the manufacturer as an adjustment, for the straight profile is the best for minimal friction and wear. Continue checking and making corrections until the side-to-side movement of the keyboard is uniform, and the movement is as small as is practical given the actual set of circumstances of that piano. Even if the key moves up and down freely, but without adequate side-to-side movement, some should be created, for it's possible that weather changes will create a sluggish action without that small safety factor. You'll need the tool for turning the pins, the key easing pliers, the Yamaha CF tool, and possibly some polish to clean the front rail pins. This step, coupled with the next two, will provide a keyboard that gives the pianist a sense of confidence as the keys are played. For now, they will not only move up and down freely, but remain stable and firm to the touch. This completes step number 4. This bushing is found on the top and in the center of the key and is called either the balance rail bushing or the center rail bushing. The reason for its existence and the purpose for the adjustment is very similar to the front rail bushing. That is, to hold the key in position and still allow free movement. In the preliminary stages, one should carefully observe both the condition of the felt and the condition of the balance rail pin itself. If lubrication is necessary, Yamaha has found the use of pure silicone oil to be satisfactory. It needs to be thinned to the desired consistency with high-grade naphtha. Checking for accuracy is done by placing 2 fingers on the key button, one fore and one aft of the pin. The key is then pushed alternately from the bass side to the treble side to detect any rocking movement from loose-fitting bushings. The amount of free movement should be very small, perhaps 1 or 2/10 of a millimeter. It's better to move quickly from one key to the next so that a number of keys are compared with each other instead of trying them slowly one by one. The final result should be a uniform, very slight rocking movement on all keys. If the fitting is just a bit too tight, using the broad wedge end of the Yamaha CF tool can be recommended. The wedge will spread the 2 sides apart as it is gently forced into the hole. Minute adjustment and great control is possible with this tool. If the bushing is very tight on the pin, instead of using the Yamaha CF tool, use key easing pliers instead. However, instead of the bushing being too tight, usually the side-to-side movement is too large. The broad end of the CF tool can be used in such a way that will compress the wood on each side of the hole. As the wood is compressed, it will move into the hole a bit, making the hole smaller. Obviously, this can only be used when a small adjustment is needed and doesn't take the place of rebushing when that is really the problem. Continue checking and making corrections until the keys move freely and yet the rocking side-to-side movement of the key is as small as practical and the movement is uniform from one key to the next. The tools needed are the key easing pliers, and the Yamaha CF tool. The results of your care and precision here will be appreciated by the pianist as the keys become more stable, comfortable, and predictable to the touch. This adjustment concerns the unbushed hole, the one in the center and on the bottom of the key. In many respects, it is the most important of the three adjustments. At least, this adjustment is very critical. Without the cloth bushing, there is no margin for tolerance or error. It, too, shares some of the things in common with steps 4 and 5, especially that it helps to hold the key in proper position and yet allows the key to move up and down easily. Since there is no cloth bushing involved, noise could be created if the hole in the wood is larger than the balance rail pin. This adjustment must result in a tight fit so that the key cannot be pulled forward or pushed backward. At the same time, it cannot be overly tight because the hole can become even smaller as the weather fluctuates. Perhaps this would be a good time to discuss the effects of humidity and its changes on wood in general. Imagine, if you will, the growth rings that can be seen on the end of a log. We all know that each year a new ring is added and that all growth takes place in the new outer ring. If the log is cut in some other direction than straight across, those growth rings become different patterns than just circular, and we call those markings the grain of the wood. The point to consider is that the grain of the wood is the manner in which the leaves and roots are connected for the transference of food during the growth cycle. The grain could be described without undue exaggeration as a set of tubes that allows the sap of the tree to flow between the roots and the leaves. The walls of these tubes are flexible and expand when they are full and contract when they become empty. Think of the tubes as a set of canvas hose used by firemen. When the faucets are turned on, the hoses swell up across their diameters, and when the faucets are off, the hoses collapse. Exactly the same thing happens to wood when humidity in the air fluctuates. If the moisture in the air is greater than the moisture content of the wood, some of it will be absorbed by the grain of the wood, and the tubes will swell up, making the piece of wood slightly larger than it was before. In the reverse case, when the moisture in the air becomes less than the moisture in the wood will lose some of it, and the tubes will become slightly smaller in diameter. The end result is that the piece of wood will shrink a bit. Of course, the example of tubes and hoses is oversimplified. It is used just to get the idea across. The way to check for the present condition is to raise the front end of the key about 10 millimeters, but not so high as to remove contact between the center bushing and the balance rail pin. Release the key, and if the adjustment is ideal, the key should not drop freely down the pin by the force of its own weight, but instead it should either slide down the pin or even stay at the top until a slight tap with your finger will make it descend. In other words, it should not drop freely of its own weight, for that would indicate that the balance pin hole in the key is too large. On the other hand, if almost any force at all must be used to dislodge the key from the point where it was raised, the fitting is too tight. This excessive tightness will cause resistance to key movement and increase the amount of force needed to properly play that key. Pianists have commented that an action feels spongy or springy to the touch when this condition exists. If the hole is too tight around the pin, it can be made slightly larger by the insertion of a long tapered rod, something like the handle of some capstan wrenches. Historically, the tool has been inserted into the hole from underneath the key, but there are advantages in using the Yamaha CF tool where the construction of the tool allows one to insert the tapered cone-shaped portion from the top of the key instead. This will enlarge the hole slightly and, at the same time, create the cone shape inside the key, with the smaller end of the cone at the very bottom of the key. And by placing a finger over the end of the tool, one can feel the amount of protrusion, and thus be better able to control its use. The natural movement of the key during playing will create a cone-shaped hole with the smaller end of the cone at the bottom of the key. When a tool is inserted from the bottom of the key, the cone shape becomes inverted, and thus the fitting is compromised as the key is played. Another advantage of the Yamaha CF tool is that it has an oval rather than a round cross-section. Therefore, the wood around the balance pinhole can be compressed at the points to the base and treble sides of the pin where the changes in humidity affect the grain of wood the greatest amount, without touching the wood fore and aft of the pin. Normal wear on the hole from playing elongates the hole toward the front and back of the key, so additional compression in those directions is hardly ever needed. When faced with the other extreme, where the hole is slightly too large, its size can be reduced by injecting moisture into the area. The moisture will expand the compressed cells. This procedure can be accomplished with the amount of moisture you can transfer from your tongue to the area via the tip of your finger, or with a pipe cleaner immersed in water. In extreme cases, the use of steam is an alternative. Many technicians recommend sizing the hole with a very weak solution of glue instead of using only moisture. The reasoning behind using a glue size is that the glue would penetrate the pores of the wood and once it dries will create a more stable condition. While I cannot argue with the reasoning, I would like to point out that glue is harder than key wood, and this part of the key can easily create a noise problem. The noise is created because of the lack of a cloth bushing to absorb the shock of key use. My experience, for what it's worth, leads me to believe that it's better to apply the moisture without the use of glue and avoid the possibility of creating any unnecessary noise. Since there's no pressure exerted by the wood on the pin, the compressed cells that have been reconstituted by moisture alone will remain expanded. The adjustment is quite stable without the addition of glue size. Another method used to slightly reduce the size of the hole in question is by burnishing the bottom of the key in the area of the hole. In the process of burnishing, the wood will compress and make the hole slightly smaller. Only a limited amount of remedial action can be taken with either this approach or by using moisture. Also, the key level must be adjusted after burnishing has been accomplished, or the key will rest at a lower position than its neighbors. The recommended equipment needed to do this adjustment is the Yamaha CF tool. Although a cone-shaped tool, perhaps the handle of a capstan wrench, will suffice if the Yamaha tool is not available. We have now completed all of the very important key adjustments that are needed so that the pianist will not be handicapped by a keyboard that doesn't respond correctly. The importance of these steps cannot be overemphasized. The confidence and satisfaction gained by the pianist from the feeling of a keyboard that moves freely, has a firm, stable position, and can be depended upon is critical to the creation of fine music. Having properly fitted action centers is very important, but this consideration should be a portion of preparation or repair rather than regulation. The step is placed here to remind the technician that this is the last opportunity one has to correct action centers without facing the possibility of undoing some of the following steps, resulting in unnecessary work. A few words are in order in any case. Properly fitted centers are necessary to produce uniform, solid, noise-free action movement which should be accomplished with as little friction as possible. The tests for proper fitting are many. One good one is the fitting should be tight enough to keep the flange in any position it is placed, but loose enough that the flange will move if the weight of the screw is added to the flange. With recent improvements to the surface smoothness and polish of the center pins made by Yamaha, the fitting of the new pin is as tight as ever, but the parts move more freely than before. This needs to be taken into consideration when checking center pin tightness on Yamaha pianos, because the parts appear to be a bit freer when they are correct than in other actions.
In addition to the test on the individual parts just described, one can support the entire action in such a position as to have the parts able to swing freely. By moving the action in a manner to cause the parts to swing, one can observe many parts simultaneously and thus find the obvious problems quickly. The action stack can be positioned in such a way that the whippins are almost balanced. In this position, it is possible to check the whippin flanges without removing the parts from the action rail. The jack center on the type of action used by Yamaha can also be checked by hand if the repetition spring is first unhooked. With experience and care, the problems can be found. Remedial work should be done very accurately, for properly fitted center pins are a very important part of good performance. Incorrect fitting of the center pins not only causes obvious problems like loose and noisy actions or a tight and sluggish touch, but in addition, the tone could be affected. For the tone of the piano is directly related to the pattern the string makes as it vibrates. If the center pin of the hammer flange is loose, the hammer will not strike the string as firmly as if the pinning were tighter, causing a slightly different pattern in the string's vibration. And if the pinning is slightly too tight, the vibrating pattern of the string will also be influenced, because at the moment of striking, the hammer will stay on the string a longer than normal period of time. This is caused by the hammer's inability to bounce away with normal speed. Pinning that is too loose should be corrected by repinning with larger pins. Pinning that is too tight either needs lubrication, a condition that is relatively rare, or refitting. Correction can be made by removing the pin, reaming the bushing to proper size, and repinning with a pin that is never smaller than the original and usually the next size larger. In addition to a screwdriver that will be needed to remove the flange from the rail, a full set of repinning tools and a set of center pins will be necessary. Once the center pin condition is in good order, we can proceed to step 8. The hammer striking the string could be compared with a baseball bat striking a ball. In order to hit a home run in the big leagues, it's necessary to do everything right. This means that the bat must do 3 things at the same time. It must swing in exactly the proper plane, the grain of the wood of the bat must be at the exact correct angle when the contact is made, and the contact must be made in the exact center of the ball. This step, called traveling the hammer shanks, is to action regulation what swinging the bat in the correct plane is to the home run. That is, the bat is not traveling upward at the moment of contact, where the result becomes a fly ball, or downward to become a grounder. The other 2 requirements for a home run on the piano are covered in the next 2 steps. I would like to digress just a bit and remind you that there is very little difference in the distance traveled when comparing a home run and a well-hit long fly ball. Sometimes it is only a matter of a few feet, but in the big leagues, the consistent hitter of home run makes $1 million a year and also enjoys the ego-satisfying trip of constantly being hounded for autographs, while the consistent producer of well-hit, long fly balls is often a candidate for a different occupation. As a piano technician, which of the 2 baseball players would you rather be? Well, back to the subject, hammer angle. In this step, we will make sure that the hammer, which is mounted on the hammer shank and attached to the action rail, moves upward in a path that is perpendicular to the action rail. If the plane of the moving hammer shank is at an angle other than 90 degrees as compared to the hammer rail, it will move slightly to the right or left. When this happens, the blow to the string is not as solid and the tone will be affected. Also, excessive wear will happen at the flange area, as well as to the top of the hammer and to the glue joint of the hammer, as these points constantly absorb the shock of the hammer striking the string. The reason the hammer shank will travel to the right or left is simply the center pin is not parallel with the action rail. This situation was caused at the time the center pin hole was drilled. The problem any parts manufacturer faces is the flexibility of the small drill bit used to make the holes in the wooden flange parts. As this small drill bit touches a hard grain, it will veer off of the planned direction ever so slightly. The end result is a hole that is drilled a bit out of line. One can compare a pin flange and hammer shank to a hinge. If the base of the hinge is slightly tilted, the other part of the hinge will raise at a slight angle, commensurate with the amount the hinge pin is off of horizontal. The center flange in the top row shows the problem. To correct this situation, either with the hinge or the hammer shank, you must change the angle of the hinge pin until it is parallel to the surface it is mounted upon. The adjustment is made by propping up the low side of the flange with traveling paper. This is shown by the center flange in the lower row. One type of material that is sometimes used to place under the flange is the gummed paper tape that is used for sealing packages. To check the correctness of the travel of the hammer shank, place a smooth rod, like a screwdriver blade, underneath several shanks and lift them. Start from the lowest position possible and raise the shanks to a point where they would be if they were striking the strings, or just a bit above that point. While it would be difficult to see any movement to one side or the other if you raised only one hammer shank, it's quite simple to see hammer shanks that need attention if you raise a number of them simultaneously. Even though this step is called traveling the hammer shanks, it is generally best to focus your attention on the hammers when checking this point. The hammers have only a small space between them, and any sideways movement can be seen easily by watching the change in the distance between the hammers as they are being moved up and down. Once an error is detected, loosen the screw in the hammer flange enough to insert a strip of gummed paper under the flange with a sticky surface toward the flange, and place it on the side of the flange that the hammer moves toward laterally. This paper shim will cause that side of the flange to be lifted, correcting the plane of the center pin. Retighten the screw. The length of paper strip will change the amount of correction, with a longer strip of paper making a larger correction than a shorter one. If only a small portion of the gummed paper is moistened, it will still hold its position well, and you may appreciate the added benefit of being able to remove the paper easily in case it becomes necessary. The tools used will include a screwdriver blade or other smooth rod to lift the shanks, a screwdriver to loosen and tighten the flange screw, and some traveling paper. Time and effort spent on this step will pay greater dividends than might be expected. This brings us to step 9. Here, the point to consider is the angle the hammer makes with an imaginary line drawn from the center of the hammer shank to the center of a string group, considering the shank is positioned correctly underneath the string group. If the imaginary line passes through the center of the top of the hammer angle is correct to deliver the most power. If the top of the hammer leans either to the base or to the treble, correction is needed. If we compare this step to the illustration of hitting the home run, here we have the equivalent of holding the bat in such a way as to have the grain of the wood in the bat at the correct angle when the bat hits the ball. Just as the ball player is very careful to make sure to hold the bat with the insignia upwards, signifying that the grain is at the best angle, we must make sure that the hammer is pointed directly at the string, giving us the correct and best possible angle. To check the angle of a hammer, compare it with the correctly angled hammers on either side. It is best to check and, if necessary, space the shanks evenly before you start. This will visually emphasize the problem. You will find some difficulty in checking hammer angle on those hammers that are bored to be in line with the bass strings. One good method is to compare the spaces to the left and right, that is, the spaces between the hammers, on both sides at the top
and bottom of the felt when the hammer in question is at rest, and again when it is raised. If there is a change in the proportion of the spaces in question, the angle is not correct. To correct the problem of a hammer with an incorrect angle, it is not necessary or desirable to unglue the hammer and re-glue it at the correct angle. Instead, put a small twisting force on the hammer shank in such a way as to make the hammer move to the correct angle. In fact, it should be forced to lean a small amount in the opposite direction. While you hold the hammer in this position, apply heat to the shank. The heat will rearrange the molecules, and the twist you've put into the shank to straighten it will remain. Heat can be applied by either an open flame, a set of heat pliers, or a heat gun that is made for the electronics trade. The heat gun is similar in construction and use to the hair dryer, but the outgoing air is considerably hotter. Be very careful if you use a flame. While the correction can be made that way, invariably the flame will leave a blackened shank, and most importantly, the lady of the house is usually less than overjoyed to see a bonfire in her $10,000 grand piano. There's no thermostat on the heat pliers, so if you use this method of applying heat, test them for temperature first on a sample shank. If accidentally the jaws of the pliers are too hot, it is much better to scorch a sample shank than the one in the piano. My experience would favor the use of the heat gun. You will find that a shank straightened by the use of this procedure will be as stable as its neighbors. The tools needed include a heat source, and of the 3 types mentioned, we might recommend the heat gun. Also, you will need a screwdriver and a trained eye to find the offender. This is the second of the 3 steps that are necessary to position the hammer to properly address its string group, not only for the mechanical power it affords, but for obtaining the best musical tone as well. Now we are ready for the last of the 3 steps. It is called hammer alignment. Performing this step will position each hammer directly under its string group, allowing it to deliver the most power. This position will also allow the hammer to be in correct location for the use of the left pedal, or shift pedal as it is sometimes called. As the action is moved with the use of the shift pedal, of course, each hammer is moved the same amount. Imagine one hammer positioned too far to the treble side of center. Since it is already too far to the right, it is obvious that as it is shifted further by the use of the pedal, it could easily end up hitting strings of 2 different pitches. One might compare the hammer hitting the exact center of the string group with a baseball player's bat hitting the exact center of the baseball. Only in this way can the player hit a home run, and correspondingly, the only way the pianist can get all the tone and volume from the piano. Whether the hammer hits 1, 2, or 3 strings, it should be centered directly under its string group. In order to best observe the hammer's position, it is necessary for the hammer to block against the string. This can be done by raising the hammer until it touches the string by simply pressing upwards under the jack. Normally, the hammer would not block against the string, but rather the jack would escape and allow the hammer to let off and drop. However, the jack can be forced in such a way as to make the hammer block against the string. This is accomplished by pressing the jack tail into the let-off button with enough force to compress the cushion and thus temporarily raise the let-off adjustment. If one experiments with the following procedure, the way to block the hammer against the string will become more apparent. Place your index finger under the jack tail in such a way that the tip of the finger is well under the jack tail, perhaps at a spot just below the center pin of the jack. While the following example should flow in one fluid movement, here it is described in 3 distinct steps for better comprehension. First, lift the jack tail until it touches the let-off button. Then, forcefully press the jack tail further into the let-off button by pressing upwards with the second joint of your finger. Press only at the spot where the tip of the jack touches the let-off button. and do not press upward with the tip of your finger yet. That would make the jack rotate. Finally, while holding firm pressure against the let-off button, carefully lift under the center pin with the tip of your finger, and you'll find that the hammer will rise and block against the string. Care must be exercised to freeze the finger movement as the hammer first touches the string, and do not lift any further with the tip of your finger or the jack will escape. If the jack does escape, immediately release all the pressure with your finger, let the whippin fall, and start over again. Obviously, the let-off adjustment must be fairly close to the string, or it will not be possible to force the adjustment far enough to accomplish blocking the hammer against the string. Let's see how this works at the piano. First, depress the right pedal to remove the dampers from the strings. This will allow you to see the striking point of the hammer better. Next, block the hammer against a string. Once the blocking has occurred, observe the position of the hammer in relationship to its alignment with the string group. Next, with chalk, identify any hammers that are not in perfect alignment, usually by marking on the tops of the key sticks between the balance rail buttons and the back of the sharps. In the highest sections, because of the capodiastro bar and sometimes the dampers will interfere with your vision, the use of a mirror will be of help. This next point is very important. If all or at least a great deal of the spacing is off in one direction, it's an indication that possibly the keyframe is not in the correct position at rest. You should make the correction at the keyframe stop block. This is done by removing the screws that hold it in place, and either remove wood from the back of the block by sanding to make it thinner, or add solid material, perhaps wood veneer or hard paper stock, behind the block to make the keyframe stop block thicker. If the correction is not made at the keyframe stop block, the following scenario would happen. First, moving the hammers in the direction necessary to center them under the strings would also move the rollers from their correct position on top of the whippins. Next, moving all of the whippins to align them properly with the new position of the rollers would move the whippins out of alignment with the capstans. At that point, the capstans would be out of position and no practical way of correcting the situation, sort of like painting yourself into a corner. The stop block positions the keyframe and thus the capstans, so care should be used to make sure the capstans are in the best possible position before starting the repositioning of the hammer and whippin assemblies. If only a few hammers are incorrectly aligned to the strings, loosen the flange screw, move the hammer assembly to the correct position and retighten the screw. After all the adjustments are made, recheck each key that you have previously marked with chalk by blocking the hammer against the string once again. When correct, remove the chalk mark. Check the hammer spacing at the same time. If it is incorrect, probably some string spacing is called for. The tools needed will be a screwdriver, a mirror, and chalk. This completes the third step for proper hammer positioning. The hammers are now set to allow the home run to be hit, but a number of other items have to be considered as well. So, onward to the next step. One of the first lines that the action designer puts down on the initial set of drawings for a new action is the line that represents the height of the white keys. It is very important for the technician to set the height of the keys at exactly that measurement, for not only is the depth of the white key travel calculated from this line and the height of the black keys measured from the same line, but another very important point is involved. Raising or lowering the position of key height will change the leverage the key has relative to the whippin. Even with the same amount of key travel, a change in leverage will change the amount of movement of the whippin and will also change the touch weight. An action model will better illustrate this point. If we focus our attention at the spot the capstan contacts the whippin heel cushion, it can be seen that raising and lowering the key height changes the point of contact between the whippin and the capstan. Notice how the capstan moves toward the back of the Whippin as the key is raised, and conversely, how the capstan moves toward the front of the Whippin as the key is lowered. This particular point has great significance in the leverage system of the action design. To illustrate that point, let's imagine a robot constructed in the image of a man to be the door opener for a business building. As the public approaches the door, they walk through a light beam that directs this man-like machine to push the door open. Let's pretend the engineering department has calculated that the robot's hand is to push on the door at a point 2 feet from the hinge, and the mechanical hand would extend 18 inches when the light beam is broken. For our purposes, let's agree that these measurements would open the door the correct amount to allow the public to enter the establishment. We are given the ideal tool, the robot, and the ideal set of specifications to make it work. However, what if we place the robot too close to the hinge side of the door as we install the device? Now the mechanical hand is at a spot 1 foot from the hinge instead of the original distance of 2 feet that was specified. Now what happens to the amount the door opens when the robot extends its hand the same 18 inches it was programmed for? Obviously, the door will open a greater amount, unless it was already opening the limit. And of course, if we try to exceed the limit of anything, something could break. Will there be any change in the pressure against the hand that pushes the door open? Obviously, the pressure will increase also. If we use this illustration of the robot and compare it with an action model, the capstan becomes the hand and the Whippin becomes the moving door. As you can see, as the key height becomes higher, the movement of the capstan further under the Whippin moves the contact point closer to the flange pin of the Whippin in just the same way the robot's hand was moved closer to the hinge of the door in our illustration. If the capstan starts out of position like this, the Whippin will be moved a greater amount, and the pressure required to depress the key will also increase. If we leave the illustration and get back to the actual step of setting the height of white keys, we'll find that in this program the key height is covered in 2 steps. Here we will set the samples, and in the next step we will level the keys between those samples. The purpose for correct key height is threefold. First, proper key height will provide correct key movement to fulfill the leverage requirements dictated by the engineering design. Next, there's the need to fit the action in the piano, and the physical restrictions like the relative height of the bottom of the fall board and the top of the key slip must be taken into consideration. And lastly, correct and exactly level keys provide beauty for the eye to behold. While the key height can be set by the information gained from checking the physical restrictions of the piano, because of the amount of latitude that exists, a measurement set this way is at best a guess at what the designer calculated. The exact measurement should be obtained either from the manufacturer or from a thorough understanding of aftertouch and its ramifications. Aftertouch is covered as a separate subject in this series of technical programs, so for this reason, we will suggest that you get the specification directly from the manufacturer. In the case of Yamaha pianos, the underside of the white key covering should be 64 millimeters above the key bed for all grands except the concert grand, where the larger size of the key stick requires that the measurement be 66 millimeters. One note of caution: the measurement is to be taken from the top of the key bed, and in almost all cases the manufacturer has removed some wood from along the front of the key bed for the key slip to fit into. The bottom of this depression is not the top of the key bed, and you must be careful that you take your measurement from the proper place. A small ruler called a machinist scale is the tool most often used for measuring key height. If one is going to use a long enough straight edge to rest on key number 1 and key number 88, only those keys need to be set at this time. If a shorter straight edge is to be used, appropriate additional samples that match its length must be set also. In our opinion, the values gained by the use of the shorter straight edge make it preferable to the long one. Using this procedure allows for and requires the key height is set in the piano, but does not require removing the hammer action from the key frame in order to insert or remove paper punchings at the balance rail. We feel that having the action completely assembled during this procedure is the better way, for the screws in the feet of the action brackets secure the action stack to the key frame and thus help to stabilize the key frame from warping. Also, the exact weight of the action parts on each capstan is much more accurate than a set of leads placed on the keys to duplicate the weight of the missing action parts. To place punchings on the pin, usually you would have to remove the key and place the punching over the top of the pin. With this procedure, a cut punching is slipped around the balance pin without removing the key. To illustrate, we will show a simplified sample of the method so that it is easier to comprehend. First, cut the punching, using a straight line from the outer edge of the punching directly into the center of the punching. The cut punching can be grasped by a set of tweezers in one of two ways. One way is to hold the punching with the cut downward at 6 o'clock. With the tweezers, grasp one of the legs at about 3 o'clock. Holding the punching in this manner, one can position the punching either in front of or behind the balance rail pin. By rotating the wrist, sort of hook the leg that is not being held by the tweezers around the pin. Let's watch that again. Another way is to hold the punching with the cut at 9 o'clock. Take the tweezers and grasp the punching at 3 o'clock on the opposite side from the cut. While holding the punching with the tweezers, spread the cut parts of the punching slightly, moving the upper leg towards you and the lower leg away. In this position, the punching can be aimed directly at the pin, and as the legs of the punching pass on either side of the pin, rotating the wrist counterclockwise will slip the punching into place. Now let's try that on the action. After estimating the punching size required, pull the action out of its position on the key bed, raise it to almost a vertical position. Separate the punchings found on the pin of the key in question to make room for the new one. From the underside of the action with tweezers, insert the properly cut punching by slipping it around the pin. If a punching is to be removed, simply grasp it with the tweezers, and if it is not cut already, tear the punching to take it out. A note of caution is called for at this point. When the action is in a vertical position, with the back rail of the action resting on the key bed, exercise extreme care not to scratch the front beam with the drop screws. If you establish a habit of lifting the action not fully up to the position of balance, but just enough necessary to be able to do the work comfortably, the drop screws cannot get into that dangerous position. With the action in this position, it will be necessary to have the action lean against you as you work. The position is actually quite comfortable and gives a certain feeling of security and control as it leans against you. You will need a machinist scale, a set of tweezers, and some cut punchings. If inserting punchings underneath the keys is new to you, a little patience will be required also. But don't give up on this procedure just because it may be new and novel, for you will find that it is not only easier to do the job this way, but also the end result is more accurate. The extra accuracy comes from the fact that the hammer action assembly is screwed in place, stabilizing the key frame, and each key is depressed into the back rail cloth by the individual weight of its own whippin and hammer assembly. The usual procedure of removing the hammer action from the key frame and attaching a set of uniform lead weights to the keys to replace the weight of the parts does not take these points into consideration. We should now have the key height set correctly in all of the sample keys. Let's move on to the next step, that of leveling the remaining keys between the samples we have just set. As was mentioned in the last step, here we will level the keys between the samples already set. If the tool you use is a long straight edge, one that will cover all of the white keys at one time, it was only necessary to set keys number 1 and number 88 during the last step.
If you use a shorter straight edge, as we are suggesting, then additional samples have to be set. Here again we will find the purpose for correct key height is threefold. First, proper key height will provide correct key movement to fulfill the leverage requirements dictated by the engineering design. Next, there's the need to fit the action in the piano, and the physical restrictions like the relative height at the bottom of the fallboard and the top of the key slip must be taken into consideration. And lastly, correct and exactly level keys provide beauty for the eye to see. In fact, this step is just a continuation of what we have done before. The end result of steps 11 and 12 should be a straight line formed by the tops of the white keys that is parallel to the key bed at the proper distance above it. In step 11, the correct height was set on samples. The goal now is to first find any keys that are higher than the samples. To do this, hold one end of the straight edge over and just touching one of the samples. Raise the other end of the tool and let it drop. Repeat this several times and look for movement. It is easier to see any movement by focusing your attention on the bottom of the keys. That area has sharp and precise edges, rather than the more rounded edges of the top of the keys. Make appropriate chalk marks on the keys that need paper punchings removed. Raise the action carefully. Do not raise it so high as to scratch the piano with the drop screws. With tweezers, remove punchings as indicated by the chalk marks. Now that the taller keys have been found and corrected, hold the straight edge stationary over a section of the keys and observe any keys that are lower than the bottom of the straight edge, and mark the lower keys with chalk. Be careful that the weight of the straight edge does not depress any of the keys. Raise the action and from underneath, first spread the punchings, then pick up a cut punching with the tweezers and insert it around the pin as you did in setting the samples. Of course, if major work is to be done, it may be appropriate to remove the hammer action from the keys and place uncut punchings over the top of the balance rail pin with the keys off, instead of spending the extra time necessary to insert cut punchings with tweezers. However, you will probably find that a few final punchings will need to be inserted even after a careful job of leveling has been done with the action off, for the procedure described in this step is more accurate. As you hold the straight edge over the keys, continually check to make sure the entire top surface of the key is parallel to the tool. When you find one that is not parallel, use the end of the straight edge to move the balance rail pin either to the bass or the treble by placing one end of the straight edge on the balance rail pin and tapping the other end of the straight edge with the heel of your hand. This motion will tilt the key in the desired direction and make its surface parallel to the straight edge. The squaring is best done as an integral part of the leveling process rather than a separate procedure. After you have made any change, depress all the affected keys with a glissando type motion to make sure they are properly seated before the next check. The tools you will need are a straight edge, tweezers, punchings, and a pair of scissors to cut the punchings. This job deserves precision, for all white key travel starts at this point, and any differences in key height will result in differences in key travel. The hammer travels approximately 5 times the amount the key travels, thus any error is multiplied. Let's move on to the black keys. The purpose for leveling the black keys is exactly the same as for white keys. That is, to fulfill the leverage requirements dictated by action design, to allow the action to fit into the piano, and to provide the beauty of uniformity. Setting the height of the black keys is done in a manner very similar to setting the height of the white keys. The only real difference is that the height is measured from the white key instead of the key bed. In the case of Yamaha actions, the height of the black key should be 12 millimeters. This is measured from the top surface of the white key to a straight edge placed on the flat portion of the top of the black keys. As in the last step, first we must find any keys that are higher than the samples. To do this, hold one end of the straight edge over and just touching one of the samples. Raise the other end of the tool and let it drop onto the second preset sample. Repeat this several times and look for movement of keys that are tapped as the straight edge falls. In this manner, it is possible to find any keys that are higher than they should be. Make appropriate chalk marks on the keys that need paper punchings removed. To correct, you would raise the action and with the tweezers remove any punchings as indicated by those chalk marks. Once the taller keys have been found and corrected, place the straight edge over the same section of keys and observe any that are lower than the standard. Be careful that the weight of the straight edge does not depress any keys and mark the lower ones with chalk. Remember, first correct the higher keys, then the lower ones. The tool list has not changed. You'll need a straight edge, tweezers, punchings, scissors, and a machinist rule. Check with steps 11 and 12 for any details you might wish to review. It is very unusual to find keys so poorly spaced that they touch one another. Therefore, the purpose for this adjustment is for beauty alone. Use the following as your goal. All white keys should be equidistant from each other, especially at the front of the key, and the black keys should be centered in the area left for them by the white keys. Spacing keys is controlled by the front rail pin. If the pin is leaning to one side or the other, naturally the front of the key will be moved in that direction. To correct this, you should use the front rail pin regulating tool. Place it under the punchings next to the wood of the key frame and carefully bend the front rail pin toward the bass or the treble until the desired effect has taken place. If the tool is placed on top of the punchings, it could deface the pin, resulting in injury to the bushing cloth of the key as the key is moved up and down. For the majority of cases, your concern should be focused on establishing the correct spacing at the front of the keys. But do be aware that any movement of the key at the front has an almost equal movement of the back of the key, but in the opposite direction. Check to make sure that friction is not caused by the back end of the keys rubbing against each other after the adjustment. And check that the capstan is left in the correct position under the cushion in the Whippin heel. The only tool needed will be the front pin regulating tool. It should also be mentioned that incorrectly spaced keys take on the appearance of improper key height. The reason is that a key that is incorrectly spaced will show a different amount of depth of key covering if viewed from the side. If the eye sees a different amount of key covering, it will assume that the key is not in the same plane as the others. Thus, it will look like poor key height. The adjustments made on the keys are as much for the pianist as they are for the piano. The keys are the only action parts touched by the pianist, and with the keys, the performer must control the creation of music. Of course, the adjustments are for the mechanical part of the action design as well, so each has to fulfill two different sets of requirements, perhaps with different tolerance ranges. The amount the key travels is one of the most important adjustments. Its main purpose is to provide correct and uniform touch, and the uniform part of the definition should be stressed. For differences in key travel are serious obstacles in the path of the pianist, especially if the differences are on the same piano. To check the amount of key travel, one can proceed in several ways. The Yamaha specification of 10 millimeters is to be measured at the front of the key. Measure the key dip block at the thickest end and make sure it measures 10 millimeters at that point. Place the block on the key to be measured with the thickest part of the block
lining up with the front of the key. Proceed by depressing the block and comparing its surface with the surface of the adjoining key. Tracing your finger across the two surfaces will indicate whether the key travel on the key in question is correct, too small, or too great. By adding or subtracting paper punchings at the front rail pin and under the cloth punching, you can change the distance the key travels until the two surfaces are perfectly level. If the block is slightly thinner than the standard, something in the neighborhood of 1/10 of a millimeter, some technicians find it very helpful for accuracy. The reasoning behind using a thinner block has to do with the beveled edge on the key covering. In such a case, the top surface of the depressed block will be slightly lower than the key height of the key you are comparing it to. There will be a slight raised portion of the key that can be felt as a bump, instead of the level surface comparison as described before. To set a uniformly correct set of keys, just continue creating the same condition of the key being slightly higher than the block on all of the other keys. To make an adjustment, lift the key the smallest amount necessary and add or remove paper punchings of the correct size underneath the cloth punching until the standard is met. In order to lift the key the required amount, it will be necessary to first remove the key stop rail from the action. Final check can be made by depressing 3 adjoining white keys and comparing the height of the center key with the other 2. Several questions should be considered in order to obtain maximum accuracy when checking white key travel with a key dip block. First, is the block that is being used the correct thickness to match the specification of this particular piano? To verify, all that is necessary is to carefully measure the key dip block and to know the manufacturer specifications. Next, does your technique assure that the block will be placed at the same relative position on all keys? If it isn't, the readings will be different even though the key travel is correct. You can solve this problem by allowing your thumb to extend below the bottom surface of the block to act as a stop when placing the block on the keys. In this manner, the block will always be placed in the same location on all keys. Is each key being depressed with the same force? If not, the measurement will change. Here you can use your sense of pressure, but another technique is to listen to the volume of the sound that is being produced as you move from key to key. If you can obtain equal volume, the force used to depress the keys will also be equal. Another suggestion is to move quickly from one key to the next so that the individual differences in key travel become more apparent. Finally, find a spot on the block that is the most comfortable for you to trace your finger across while making the test. Always use the same spot, for unless the taper of the block exactly matches the geometry of the space created when the key is depressed, the block will give different measurements along its length. It is unusual for a key dip block to exactly match the piano's geometry. Therefore, this point is of importance for precision. When inserting the punchings, it's a good habit to arrange the punching order with the thickest on the bottom, graduating to the thinnest on the top. Of course, the cloth punching is on top of all of the paper punchings. If the paper punchings are organized in this manner, it's very easy to find the punching you need. You will need a key dip block, a tool to measure the thickness of the key dip block, tweezers, and the appropriate paper punchings. One more bit of advice. Do not place the paper punchings on top of the cloth punching with the thought of returning later and putting them under the cloth punching. Do it correctly the first time. Then you can proceed immediately to step 16. Step 16 will assure that the Whippin is correctly positioned and fulfills alignment considerations at 3 different points of reference. And those points to be checked are that the repetition lever is centered under the roller, the tail of the jack is centered upon the let-off regulating button,
and the Whippin support cushion is centered over the capstan. The Whippin transmits the energy from the key to the hammer assembly and must be properly aligned in order to correctly fulfill its mission. Raise a full section of hammer assemblies so they stand alone. Lower each one separately and observe the three standards just mentioned. When correction is necessary, it can be done three different ways. The choice is determined by the problems encountered. First, the Whippin could be shifted to the new position. In this case, the flange screw is loosened and the Whippin is shifted to the bass or treble and the screw retightened. The amount of shift available is determined by the size of the flange screw hole. The flange can be shifted until the side of the screw hole touches the screw. In a few extreme cases, where it would be to your advantage to shift the Whippin a greater distance than possible with the parts in their present condition, it is possible to allow for more movement by enlarging the hole in the flange. This can be done by using a small round file to enlarge the hole in the flange. In the case of shifting, the 3 points used for checking the alignment of the Whippin are all moved the same amount. Those 3 points are the matching of the repetition lever to the roller, the contact the jack tail makes with the let-off button, and the position of the Whippin support cushion over the capstan. The second adjustment could be called swinging the Whippin. In this case, traveling paper is added to one side of the back of the flange in a manner that would remind one of putting traveling paper on the hammer flange for traveling hammer shanks. The traveling paper is placed under one side of the flange and therefore changes the angle of the flange, or more importantly, changes the angle the center pin has in relation to the Whippin rail. Such a correction will swing the Whippin, moving the area where the capstan touches the least and the jack tail area is moved the most. This procedure is used when the 3 points to be checked each need to be moved a different amount from the others. The third method of adjusting will rotate the Whippin on the axis of the flange screw. If the Whippin flange screw grips the flange at the time of final tightening, the flange will rotate with the screw and move the repetition lever on top of the Whippin in one direction while moving the bottom part of the Whippin in the opposite direction, where the support cushion contacts the capstan. The jack is in approximately the same plane as the flange screw and therefore doesn't move much at all. The top of the unit does most of the moving. If this condition exists, correction can be made by loosening the screw, rotating the Whippin to the correct position, and retightening the screw. Sometimes it is necessary to force the rotation a bit by placing traveling paper under one portion of the end of the Whippin flange. During the process, check the jack to make sure it is centered in the repetition lever slot. If not, corrective measures should be taken. Remove the Whippin and support the side of the Whippin that is directly under the jack and on the side of the Whippin that the jack needs to be moved toward. A light tap directly on a properly protected jack top will correct the problem. A support tool can be made that will accomplish the proper support without removing the Whippin. To accomplish step 16, you will need a screwdriver, some traveling paper, a small round file, and a small hammer. During the earlier steps, we made sure the hammer properly addressed the string and stated that the hammer could be compared to a bat about to hit a home run. Using that same baseball comparison, step 16 would be setting up the ball player holding that bat. His stance, distance from the plate, feet placement, and so forth are now in the best position, and we can turn our attention to step 17.